Okay, hello everyone, and welcome to the tutorial for the build drive design. In this tutorial, we're going to talk mainly about the V-build design, and we're going to have a look first about some of the important equation we're going to use for this one. I know it's been covered to you earlier in the equation in the lecture slide, but it's going to be a good idea to go through them once again. So first, the V-build is designed to operate without slipping on smooth V-shaped grooves in these sheaves. And this is the most popular among all the other build drives, and a typical arrangement of the elements of the V-build drive is shown in the figure below. The standard V-build cross sections are given here. You can see that most of the dimensions are written in the inches unit, and the figure 710 is for heavy duty industrial V-builds. The 711 is industrial narrow section V-builds. 712 is the high light duty fractional horsepower V-builds, and the final one is going to be for the automotive V-builds. The next slide shows you a copy that I extracted from the older version of the book, where the dimensions are given in millimeters. Now, when you read these standards or these tables, you can see that it's been given that the upper one is going to be the inches sizes, and the metric sizes numbers is going to be usually a number plus a letter. So the analysis of the V-build drive starting by equating the vertical components of the pulley groups, and simply we are going to find a relation for the friction forces, and then we start to calculate the other parameters. The first equation we're going to start with to do the calculation is going to be the following: that the torque 1 tension 1 minus the m multiplied by the v square divided by the T2 multiplied by the m multiplied by the v square is going to be equal to the exponential of the mu theta divided by the sine alpha. The power equation will also going to have the same scaling of the coefficient of friction for the V-builds. We can calculate the build speed, or the VB, by using the equation that the V build is going to be equal to d1 omega 1 divided by the d2, and this will be equal to d2 omega 2 divided by 2. Also, we can arrange the equation from the omega 2 change to the RPM is going to be the pi multiplied by the diameter multiplied by the RPM divided by 12. That's in the case of the feet per minute. If I'm going to do that, I divide by 1000 and having diameter here in millimeters instead of the inches, I'm going to have the VB to be given in meter per minute. The angular velocity of a ratio of the sheaves is going to be equal to the omega 1 divided by the omega 2, or the diameter 2 divided by diameter 1. The relationship of the pitch length, or the L, the center distance C, and the sheave diameter D's are given in the following equation. Usually we are going to calculate this value for the length, and then we can simply choose from the standards that are available in the table 7.2, and then calculate the C again based on the fixed of L. So the center distance now is given by the equation that the C is equal to the B plus under square root of the B squared minus 32 multiplied by D2 minus D1 squared divided by 16, where the B is given by the following equation, and the recommended value for the C is going to be more than D2 but less than 3 multiplied by D2 plus a D1. The length of the span between the two sheaves can be calculated with the following equation, and the angle of the contact of the belt on each sheave can be given by the equation for theta 1 and theta 2, where the equation is actually the same, except that we are going to have plus and minus, where the theta 2 should be more than 180, while the theta 1 should be less than 180, and the total of the theta 1 plus theta 2 should be equal to 360 degrees. So we have a drive design procedure, which is going to be: first we need to find the rated power of the driving motor and base the sizing on this. Then we need to find a service factor based on the type of the driver and driven load, calculate the center distance with the nominal range of that the C is going to be more than D2 but less than 3 multiplied by the D1 plus the D2. Find the power rating for one of the belts as a function of the size and speed of the smallest sheave. Then find the belt length, then choose the standard size. Do the sizing of the sheaves, use the standard size, and the most commercially available sheaves should be limited to 304.8 meter per minute up to 1981 meter per minute. The belt length correction factor should be applied, and the angle of the wrap correction factor should be also found, where the angle of the wrap on the smallest sheave should be greater than 120 degrees. Decide what the number of the belts should be used and find the initial tension in the belts. Some of the design data requirement is first find the rated power of the driving motor, find the service factor based on the type of the driver and driven load, find the center distance, belt length, the size of the driving and driven sheaves, and the nominal range of the center distance should be found. So let's take a look to the first example for the V-belt design. First, we've been given that electrical motor with a normal torque and rated at 37.32 kilowatt at 121.45 radian per second. So this is the output of the motor. The full load speed to drive the pocket elevator in a potash plant for 16 hours a day at 70.67 radian per second. This will be the output speed. Design the V-belt drive for this system. So we said that the first step should be doing the calculation for the design power. To do that, we need to find the correction factor for the belt. So, service factor for the belt. So the table 7.1 give you the V-belt service factor depend on the type of the driving machine and the driver type. So what we have was that we have an AC motor, normal torque. So we have a look here where we can find that. For driven machines, take a look where we can find a pocket elevator. So we're going to find it at the moderate shock loading pocket elevator. We take a look to the columns, we can see that we have an AC normal torque, and this is AC high torque. For our case, it was normal torque, so this should be the one. And we say it's going to be operating more than 15 hours a day because it's operating for 16 hours a day, and thus we can locate that the value for the service factor is going to be 1.4. Now from there I can do the calculation for the design power, which is going to be equal to the actual power or the input power multiplied by the service factor. So it's going to be equal to 52.25 kilowatt. Now the type number 2, we need to find what will be the belt type. So in the SI unit we can find mainly the 3V, the 5V and the 8V. And we have the extension of that, which is going to be the VX. Now let's see on this chart what do we have and what we can use. Remember that we calculated the design power. So we start taking a look to the bottom on the x-axis and locate our design power. Second, you can simply use the speed of the faster shaft, which is going to be the input, of course, and it was in the input. Anyway, I don't remember that, but anyway, we can start to do the calculation. The speed was 121.45 radian per second, which is equal to 1159.7 RPM. So we can simply find the value for that, which is located at 1160 and intersecting with the 70 design power. And then we're going to have the intersection at that point, which is going to be located within the 5V. So we can choose the 5V as our belt type. Now, next step, we need to calculate the speed ratio. So it's going to be equal to the omega 1 divided by the omega 2. The omega 1 was the 1160, while the output was 657 RPM. So we can do it either in RPM or the RPS, which is radian per second. At the end, we are going to get that the ratio will be equal to 1.72. Now, step number 3, we need to determine the sheave sizes. So we're going to choose that the build speed of 1219.5 meter per minute is going to be applied. So how we got this one? This is the range, because the range is going to be anything between 304.8 meter per minute and less than 1981 meter per minute. So we choose something like the 1219. Actually, this is a specific one because this has been changed from the feet per minute to meter per minute. So now, with the equation tell me that the VB is equal to pi d1 n1 divided by 1000, and this will be equal to the 1219.5 meter per minute that we selected. Now the velocity is known, pi is constant, diameter is known, n1 is known, and we have 1000 is a constant. So what's the point? No, the point is that the d1 is not known yet. I need to determine the sheave size. So I can rearrange this equation to be as following, and then I'm going to find that the value for the diameter 1 is going to be 334.5 millimeters. Okay, now I know what the speed reduction ratio and or the speed ratio, and then I can calculate also the output diameter, or the D2, which is going to be equal to 574.86 millimeters. So now I found the diameter 1 and diameter 2, and this will open the door actually to calculate the center to center distance. Now the step number 5 is going to be find the sheave size. So that's what we have for the 5V or the 15N, that's in the metric system. It's going to be the one with a dimension of 5 and 0.8 and 17.32. Actually, that's not how to read the inches, but in general that will be distance. So we must find an acceptable standard sheave 1, and then corresponding the acceptable sheave 2. So I got that from a different reference about how to do that. So the narrow section of the V-bolt are identified by their pitch length. For example, if I'm going to have the XPZ 987 has a pitch length of 987 millimeters. So in order to calculate the pitch length of the belt, you must measure the inside length, which is the circumference, and then add a figure depending on the section size as listed below. So for the SPZ value is going to be 13 millimeters. For the SPA is going to be 18 millimeters. For the SPB is going to be 22, and for the SPC is going to be 30 millimeters. Now we are going to continue exploring what is the sheave size. So we must find the acceptable standard sheave 1 and then corresponding acceptable sheave 2. So let's see how we can read this one. These are the standard driving sheave sizes from for the D1, and this is the approximate driven sheave size, which is 1.72 D1 in millimeters. We have the nearest standard sheave 2 and the actual output speed in radian per second, which is something I have. We said it should be 72. Okay, sorry, 70.67. So in that case, I'm going to choose these two sizes, okay, which are going to give me the output speed to be 60.67 radian per second. They both look okay, and we will try the larger one, which is having the diameter 1 of 315. So the 315 is actually 12.4 inches. Now we're going to find the rated power, and this can be done by using the figure 715 for the power rating of the 5V belt type. So we have the small shear pitch diameter, now it's found, and here we can simply connect between the different standard shear pitch diameters, and we can simply have the intersection as going. We got the RPM value is around 1160 RPM, and the diameter, diameter 1 is 12.5 inches. Now we're going to find that the power rating is going to be equal to 26 horsepower, or what's equal to 19.4 kilowatt. So the required rated power is 37.2. So how to overcome this problem? We can use 2 belts or 3 belts in order to take all the load to the other pulley. Now 37.2, this 19.4, so I think 2 belts can be suggested at the beginning. Now we are going to adjust the speed ratio to get a total power or the belt numbers. So take a look to this diagram. Once again, this is the 1160. We know the speed ratio of 1.7 or 1.72. We make the intersection between them. That will be the point. Then I can find what will be the power added to the rated power. So we are in the range of 1.18. Okay, about, I'm not sure about this figure. Yeah, so we use here 1.15. I think it's 1.8. So the power added to the rated power is going to be equal to 0.859 kilowatt. And then the total power in that case will be equal to 19.68 that we calculated earlier, plus the 0.859 kilowatt. And that will make the total power to be equal to 20.5 kilowatts. Okay, now we have total power. Let's continue and find the estimated center distance, because we know the 2 diameters, and we start the calculation from there. So the size of the center to center distance should be more than the diameter 2 size, which is 535.9, and less than the 3 multiplied by the sum of the 2 diameters, which is 2552.7. So now we should do something in between. So for the interest of conserving the space, we are going to try that the C is going to be hardly more than the D2. So I'm going to take it as 609.6 millimeters, for example. Now we are able, by knowing the C, we are going to be able to find the required belt length. So now the C is known, the diameters are known. Now we can apply this equation to find that the length of the belt is going to be equal to 2,575.6 millimeters. Now that's almost equal to 101.4 inches. So we are going to use this value to find the most proper length that can be found for the 5V type of the belt. So for the 3V and the 5V here, we have 95 maximum. For the 3V, 5V and the 8V, we can get the 100. So I can choose the 100 inches now. I'm not going to go to the 106, because in that case, I need to enlarge the center to center distance. So we're choosing the 100 inches length. Now we are going to calculate the actual center distance based on the value of the length that we have. So again, to go backward, by first calculating the B. Now this is the one we got from the standards, which is going to be 100 inches or the 2540 millimeters, plus the 2 pi multiplied by the D1 plus the D2. So the B is going to be equal to 4,816 millimeters. Now calculate the actual C, and you are going to find it to be equal to 591.8 millimeters. The one we got earlier was 606. Now, by knowing all these values for the D and the C, we can simply start to calculate the theta 1 and the theta 2. So the theta 2 is going to be equal to 158. Theta 1, that's theta 1. Now I can find the theta 2 is going to be equal to 360 minus 158. Now the step number 12 is going to be determine the correction factor, and that's what we can find from the equation 718 for the angle of the wrap correction factor, or the C theta. Now simply we know what is the value for the angle of the wrap. We said it's 158. Okay, then we intersect it with this curve, and we're going to find the value of the C theta to be equal to 0.94. The same thing for the belt length correction factor. We're going to have the intersection with the 100 and the 5V curve, and we're going to get the value to be equal to 0.96 for the CL. Now, by using these correction factors, we can find the corrected power value. So the C theta multiplied by the CL multiplied by the power value plus, of course, the added power is going to be equal to 18.54 kilowatt. Now we're going to calculate the belts number needed. So in that case, the number of the belts So the number of the belts needed is going to be equal to design power that we calculated earlier, divided by the corrected power belt we got. So design power we got was 52.248 divided by the 18.53, and this will tell me that the number of the belts is equal to 2.818. So definitely we're going to use 3 belts to do the job. So in summary, we're going to have the diameter 1, diameter 2, the belt length, the center distance, and the number of the belts needed. Now the second example, we're going to have a different scenario. So this will include the coefficient of friction in the calculation, and we know the density of the build material. We need to find the power can be transmitted. We need to know what will be the I think the mass as well and other stuff. So let's have a look. We have a built drive consists of 2 V-belt in parallel. So we know that we have 2 belts on a grooved pulley of the same size. The angle of the groove is 30 degrees, and the cross-section area of each belt is given as 750 millimeters square. The coefficient of friction is 0.12. The density of the build material is 1.2 megagram per cubic meter. That's the density. So, and the maximum safe stress of the material is 7 megapascal. We need to calculate the power that can be transmitted between the pulleys of 300 millimeter diameter rotating at 1,500 revolution per minute, and find also the shaft speed in revolution per minute, at which the power transmitted will be at maximum. So the data given was the maximum stress, the maximum tension can be found through that, which is simply, we know that the pressure has been given to us here, or the maximum safe stress is 7 megapascal, which is equal to the force, or the force of the tension divided by the cross-sectional area. So the stress given as 7 megapascal, or 7 multiplied by 10 up to the power 6, multiplied by the cross-sectional area, which is 750 multiplied by 10 up to the power minus 6 meters square. So we are going to have 5,250 Newton is the amount of the force. The density of the built material is 1.2 megagram per square meters, and the specific mass of the built material in that case is going to be equal to rho times A, or the density multiplied by the cross-sectional area, and this will give me what will be the mass per unit length. And I'm going to get that each 1 meter is weighing 900 grams, 0.9 kilograms. So we have two belts, so the alpha is going to be equal to 30 divided by 2, and this will be equal to 15. Also, due to the two pulleys of the same size, the contact angle is going to be 180 degrees for ordinary belt. The power can be transmitted between the pulleys can be calculated as that the power is equal to the N, which is the number of the belts, multiplied by the tension 1 minus the mass, specific mass, multiplied by the V square, and multiplied by 1 minus the exponential of minus mu theta V. And then we are going to do the derivation of that equation to get this new equation to be equal to 0. And thus I'm going to find that the V is going to be equal to under square root of the T1 divided by 3m, and that's happened when the maximum power is going to be obtained. So now we know the T1 has been already calculated at 5,250 and divided by the 3 multiplied by 0.9 kilogram per meter length, and this will give me that the velocity is going to be equal to 44.095 meters per second. From this value, I can simply extend to find the omega, because the omega is going to be equal to the velocity divided by the radius. And thus I'm going to get it to be equal to 293.97 radian per second. That's it. That's the velocity we would like to calculate. Now a third example, and in this example we need to specify the standard 3V belt length that will be applied to two sheaves with a pitch diameter of 131.25 millimeters and 348.75 millimeters, with a center distance of no more than 635 millimeter, or the 25 inches, and then calculate the actual center distance that will result and the angle of the ramp on both of the sheaves. So now the steps is going to be as following. Get what you have, okay? We have the D1, D2. We know the C value. We're going to put it in the first equation. We're going to get the length calculated, go back and find the length from the standards, and then use it to calculate the actual C value, then calculate the value for the theta 1 and theta 2. So let's see the steps of the solution. Actually, I'll just put it as one go. So in this problem, we may choose the C value to be less than 600 millimeters as a trial value to choose the appropriate 3V belt to be used. D1 is given, D2 is given. Use the equation 7.3. I will find that the length for the 600 millimeter C is going to be equal to 1,968.25 millimeters, or the 77.49 inches. I'm going to choose the standard length as the L equal to 2032 millimeters or 80 inches, since one of the 75 inches is not going to be long enough. So we use for the 3V. None here is going to be compatible. 75 is not enough. We are going to choose the 80. So this will be the standard length we are going to have. Now we are going to go back using this one to calculate the value for the actual C, rather than the one that we estimated at 600. So we need to find the C, we need to find the B first. Now the L is the 80 inches, or we can change it to millimeters. We know the D2 and the D1, and we can start to do the calculation. The B is going to be equal to 5,113.6 millimeters. Now we're going to apply to the C equation, and the C value now can be found as 629.8 millimeters, which is less than the permissible value we've been given in the question of 635 millimeters. So this should be okay. Now calculate the theta 1 and theta 2 using the two equations given to us, and we can find that the theta 1, the equation actually is the same, we said just a plus minus. I can find only one of them, then subtracted from 360. So now we can find that the theta 1 is going to be equal to 160.113 degree, while the theta 2 is equal to 199.887 degree. Double check that theta 1 plus the theta 2 is equal to 360 degree. If yes, that's it. Our calculation is correct, and then we can select our